Okay, everybody, welcome to this review of measurements and how to record measurements properly. So I just want to begin by saying that whenever you're doing a measurement, there's always some kind of uncertainty with the measurement. It could be because of the measuring device, it could be because of how you're using the device, but there's always an issue. And you have to be aware of this when you're doing things at home, with medications, and if you're not careful and take these errors into account, you could have a lot of issues. Think of if there's an issue with the dosage of a medication, that could have huge repercussions for patients. So you got to take these uncertainties into account in physics as well. As I said, the measurements that we look at, there are two types. They could be due to the instrument that you're using. Those are called instrumental. And if you think about a stopwatch versus, say, a grandfather clock, obviously the stopwatch is a much better measuring device. But there's also something called procedural errors. These are the errors associated with the use of the device. So for example, the stopwatch is a great tool, but you have to remember there's a limitation. That's going to be your reaction time. And that is going to be your procedural error. So you have to take these into account whenever you're making any kind of measurement. Now, when we are doing measurements and we're using some kind of device, it's important to remember to record your measurement properly. So what we typically do is this. We take all the digits that we know for sure, we write them down, and then we add one more that's called an estimated digit. And all of these together, what we write down, are referred to as the significant digits of a measurement. So for example, in this situation here, I've got a pencil, and this pencil, according to this measuring device, the length of it is 2 centimeters exactly. So those are my certain digits. And I'm estimating the about 0.9. So I would write down 2.9. 2 being the exact certain digit, and 0.9 being my estimated digit. Now the same applies when you're doing any other measurement, for example, liquids. So I have a graduated cylinder here, and you can see that I can definitely say it's 51.2. So 52 for certain. So I'm going to record those. And then one extra digit, which would be around maybe 0.6 or 0.7. So you write that down as 3 numbers, 3 significant digits. And of course, the last significant digit, the estimated one, could vary. Some people are going to put down 0.6, some people are going to put down 0.7. As long as it's a reasonable estimate of the measurement, you should be fine. The one thing to take into account whenever you're doing any kind of measurement is parallax. Now, parallax is basically just the shift in position of an object because of where you're measuring from. So if I'm measuring this pencil, if I'm measuring at extreme angles, the value of that measurement could be in doubt. It could be off significantly. So you always make sure you have your eyes directly opposite from the measuring point, and that way you reduce that error. This is especially true when it comes to liquids, where you have to take the parallax into account. So again, you have your eyes directly across here. So you bend down when you're making measurements with graduated cylinders. So let's practice a little bit. So remember, for each of these, what we want to do is we want to record all the digits that we know for certain plus an estimate. So what I'd like you to do is I'd like you to try doing these. So I'd like you to pause the video and estimate and record the certain digits plus the estimated digit for each of these. Let's look at the first one here. So here I know I've got my 4.1. That's certain. I'm going to estimate the next one. Maybe it's about 0.3. So 4.13. Let's see how we did. Oops, hold on here. Sorry. Okay, there we go. So I have 4.15. Again, see the last digit is the estimated one. It's going to vary slightly. The next one is going to be 3.2. So I got 3, that's for certain, and then I got the estimate 0.2. Here, I only have one significant digit, 0.9. Yeah, that's about the best I can do. In the next one here, I know I've got 44. The certain digits, and I can estimate the last one, 44.5, for example. There we go. So in each of these, what we have is we've got significant digits. Here I've got 3 significant digits I recorded. Here I had 2. Here I had only 1 significant digit. And here I had 3 significant digits. So the number of significant digits roughly represents how accurate your measurement is going to be. Now, here's a great example of how you have to take significant digits into account when you're measuring. So we had a group of students. They recorded the time it took for a pencil to drop from the desk to the floor. And they're using a stopwatch. And what they noticed is that based on the reaction time, they knew for sure they could time the object falling to the accuracy of 0.1 seconds. And then they included one extra digit just as an estimate. So in the trial 1, they had a time of 0.47 seconds. Second trial was 0.54. Next one's 0.42. So there's a little bit of a range there. So what they did is they averaged the results. And when they got the value, they found it was 0.476666. And just by looking at that, you know that that seems to be a very, very exact measurement. It's much more accurate, in fact, than the original measurements were. So you have to take that into account. So what you have to do is you're going to take that and you're going to have to round it, keeping in mind that you only can write down 2 decimal places in your final answer. So instead of writing the measurement as 0.476666, we're going to have to round right there. So we round the value to 0.48. And that takes the limitations of the previous measurements into account. And that's the whole idea behind significant digits. You have to manage the way you write down and record the accuracy that was include the limitation of the measuring device. So here's another set of examples. So let's say someone else did the measurement. You weren't around when they did it, and you want to have a sense of how accurate it was. So here's a couple of examples. So which of these do you think will be more accurate? Well, let's see. I've got 100 centimeters or 103.4 centimeters. Just by looking at it, I'd have a lot more confidence in here. And the simple reason is there are a lot more significant digits. And because there are more significant digits, this is a better measurement as a result. Now the same is true in the second example. So I've got 100 centimeters or 100.00. Why would I write down the 0.00? I'm trying to tell you that I can measure to 2 decimal places. So this is a super measurement. This one almost sounds like I'm estimating. It's about 100 centimeters. So here I'd have a lot more significant digits. So let's look at the number that we have here. So here I've got 1, 2, 3, 4, 5 significant digits I'd be fairly confident about. So 5 significant digits. Here, I'd only be confident about the 1. So I'd say this is only 1 significant digit. Only one of those digits is really valid in my measurement. And that's the whole idea behind significant digit rules, which we're going to be discussing next. We have to understand how to record and how to read other people's measurements. So here are the rules. They're very simple. All non-zero digits are significant. So anything from 1 to 9. There should be a 1 here. It's a typo. So here, I've got 1, 2, 3, 4 significant digits because all of those digits are important. They're all 1 to 9. Here I've got 1, 2, 3. So again, 3 significant digits according to this rule. Now, which leaves out the zeros. Now, zeros you have to be careful with. Any zeros between non-zero digits are significant. So for example, here, remember, 1 to 9 are significant digits. 6 and the 6 are significant. So that means that the 0 in between has to be significant as well. So this number has 1, 2, 3 significant digits. I call this the sandwich rule. Any zeros that are sandwiched between other significant digits are significant themselves. Here's another example. I've got the 2, the 9, and the 7. They're 1 to 9, so they're all significant. And you got these zeros sandwiched in between. So this means this number has 5 significant digits. Just remember the sandwich rule. Now, the other rule that's important for zeros is if I've got a trailing 0. That means a 0 at the end of a decimal. So, for example, 2.0, 2.10. These are trailing zeros. 2.100. Why would I have them there? Couldn't I just have written this down as 2 or 2.1 or 2.1 over here? I'm giving you extra information. I'm telling you that this measurement is accurate to 1, 2, 3 decimal places in this situation here. So these trailing zeros are significant. Otherwise, why would I waste time writing them down? So in this number here, I've got 1, 2 significant digits. Here, 1, 2, 3 significant digits. Here I've got 1, 2, 3, 4 significant digits. So just think of the zeros at the end after a decimal place. So after a decimal place. That's important to remember. Now, if you've got scientific notation and there's zeros there, they're all considered significant. So 2.0, 1.700, 3.50. Guess what? Why are they significant? These are trailing zeros. It's the same rule as in the previous situation. If you've got a zero after the decimal place at the end, it's significant. So it's the same rule as the trailing zero rule. It's equivalent. So let's look at a couple of situations where they're not significant. Zeros are not important parts of the measurement. So what is non-significant? If you have a decimal value and the zeros in front, they are not considered significant. All they do is they're placeholders. So for example, 0.3, the 0 is not significant. Only the 3 is. One significant digit. 0.22, got 1, 2, but this is in front. It doesn't count. So only 2 significant digits. 1, 2, this is a trailing 0, remember? But the ones in front are not significant. They don't count. All they do is they push the decimal place over. The easiest way to look at this is to write this as scientific notation. So if I had to write this in scientific notation, it would be 7.0 times 10 to the negative 3. And very quickly you can see 2 significant digits, 2 significant digits. It works out. Another situation where the zeros are not significant if they're placeholders for large numbers. So for example, say I got 30, 2200, 71,010. The zeros here are not significant. They're placeholders. So here I'd only have 1 significant digit, 2 significant digits. Here I have 1, 2, 3, sandwich rule, 4 significant digits. Let's take a look at this 2200. If I take 2200 and I write it as scientific notation, it would be 2.2 times 10 to the 3. So you can see here, very obvious, 2 significant digits, 2 significant digits. This measurement is limited to that value. The last digits are not very good. They're not really important. So remember those rules. So again, 1 to 9, all those numbers are significant, which would be the zeros. If the zeros are trailing zeros at the end after a decimal place, yes, they're important. If they're part of scientific notation, they're important. If they're placeholders, though, they're not. And you'll see a simple pattern. You'll get used to it after a while. Now, say I've got a number, and let me just go on to the next one here. No, let's just do some practice, sorry. So let's take a look at some practice. So what I'd like you to do, I want you to take a look at these. I want you to record the number of significant digits. What I'd like to do is I'd like to put a check mark over the ones that are significant. And then I continue and look at the zeros. So for example, here I've got 6, 8, 7 are significant. I got a 0 sandwiched in between. So sandwich rule applies 4 significant digits. So I'd like you to try the rest of these and see how you do. So you should pause the video at this point, try these out, and then check the answers in the next sequence. Okay, let's check our answers. So what I've done here is I've shown you the correct number of significant digits, and I've shown you the significant digits actually in red. So here, just a quick recap, these are significant, sandwich rule. These are significant, these are not, placeholders. These are all significant. These are not, placeholders. Significant, placeholders. These are significant, sandwich rule, trailing 0 rule. These are placeholders. They're not important. So you get the idea. So basically, anything that looks like this, these are placeholders. Or if you have something like this, these are placeholders. These zeros are not significant. The only zeros that are significant are sandwich rule, and if I have trailing zeros, so zeros after the decimal place at the end. These are significant, okay? Now, what if I have, there's an awkward time sometimes when we're recording measurements. Let's say I've got 100 centimeters, but I measured it really accurate. It's exactly 100 centimeters. Well, just by looking at the 100 centimeters only has one significant digit. And just by looking at it, it doesn't look very accurate. So to show that it has more significant digits, what you do is you write it as scientific notation. So I could write it as 1.00 times 10 to the 2. This would tell me this is a really great measurement. It's accurate to 3 significant digits. If I, however, I wrote it as this, I would know that's an estimate. It's not a very good measurement. So scientific notation is the way to go, the best way to do this. So what I'd like you to do, just like before, figure out how many significant digits we have here, and then rewrite the number in scientific notation. Remember the rules. Placeholders are not significant. Trailing zeros are. 1 to 9 are. So pause the video at this point and then check your answers. Let's see how we did. And what you'll notice is that when you write the number in scientific notation, the significant digits do not change. 1, 2, 3, 4 significant digits. 4 significant digits here. 2 significant digits. You notice that's the rule for all of these. So in the end, when you're writing in scientific notation, you're not changing the measurement. It's still the same measurement. You're just writing it in a different way. So scientific notation does not change the measurement. Okay, so the measurement. So it's the same number of significant digits that you record. Okay? So what I'd like to do at this point is we're going to be stopping the video. And what I'd like you to do in the next segment is take a look at how we can calculate this significant